Chapter 12, Lesson 8 on similar solids. Okay, so two solids, we say that they are similar to one another if they have the same shape and they have corresponding linear measures that are proportional. So what that means is when we're measuring like the length or the width or the radius and different measures like that, the slant height, things that are linear that we measure, they are, if all of those measures are proportional with another solid, then we say that they are similar solids. Okay, so if we're going to look at two solids, we're going to look at these two pyramids and decide if they are similar. So as what I notice is that I have the height of the pyramid drawn in, and I also have the length and width of the base drawn in. So the length and width of the base, they are both 4 and 6. All right, it's a square, so they're the same. So as what I'm going to do is I'm going to make a ratio. I'm going to say, all right, if 4 over 6 is equal to 10 over 15, because these two are the measures of the base, length or width, the same thing, and these two are both measures of the height. If the heights have the same proportion as the length of the base, then they are similar solids. So I have kind of a question mark here. So an easy way to do this is just to cross multiply. I get 60 over here, and 4 times 15 I also get 60, so they are equal. So yes, they are similar solids. Okay, now if I know that two solids are similar, then I can find a missing measure. So I can say, all right, I'm going to take this solid over here, the smaller cone, and I'm going to say, okay, the radius is 8.4. So I'm going to make that a proportion with the radius over here, 10.5. And if they are similar, then that has to be proportionate with this height, which is 16, over this height, which is x, which is what I don't know. And then I will solve that proportion. So I would cross multiply, so I would say 8.4x is equal to 10.5 times 16, which is 168. And then I would divide both sides by 8.4, and I would find that x equals 20 inches. And so I know that those linear measurements must form proportions. So when we talk about the scale factor between two similar solids, the scale factor is really just a proportion to show the relationship between two similar figures. And sometimes that proportion can get simplified down into a whole number, but other times we can just leave it as a fraction, as that proportion. When I think about the proportion, so let's say that I have, we'll just do a cube, it's easy to draw, and I have another cube over here, and I know that they're similar to one another, and this cube has a length of 6 centimeters, and this has a length of 10 centimeters. Well, I could say the ratio, the scale factor, is 6 to 10, right? If I'm talking about this cube to this cube, okay? And it kind of doesn't matter how we set them up, as long as we know we're talking about maybe the smaller over the bigger or the original over the new. But the scale factor can be written kind of either way. We could simplify that and we could get 3 over 5, but it doesn't really matter. Sometimes we also call it 5 over 3. But the scale factor is just showing that relationship. Once I know that scale factor, I can then determine the scale factor of the surface area. So if their scale factor is, for example, 3 over 5, then the ratio, the scale factor of the surface area is going to be 3 squared over 5 squared. So a lot of times we say that the surface area, put surface area, SA, of solid A over the surface area of solid B is going to equal A squared over B squared. That ratio of their scale factor is going to be squared. And then the volume of solid A over the volume of solid B is going to be A cubed over B cubed. So for example, if I looked back at my other cubes, the ratio, the scale factor would be 3 cubed over 5 cubed or 27 over 125 would be how I could set up a proportion to find one of their volumes if I knew the other one.